again, good afternoon, and thank you all for my talk today. Thanks, Professor Tiwari, for the kind introduction and my background. I'm sure most of you are very eminent to this. I mean, working in different aspects of the world fashion research. Before I start my talk, I would like to briefly mention the background of this research, and then I'll see what we started this work mainly for orthopedic implants, and then we realized that we can do it to larger way to minimize hospital-acquired infections. I'll talk about that, what hospital-acquired infections and other aspects soon. So you can see here two bugs here. You can see one small fly here, and another bug here. What you see is cicada. They're the two tropical flies, tropical flies or tropical bugs live in many parts of the world. So our research is very, very significant. These two bugs play a very, very important role on what we are doing in producing antibacterial bactericidal surfaces. It could be either for different medical implants, or it could be for, don't worry, it's okay. So the next slide will go. So it could be either for implants, or it could be for. Keep that in mind. The wings of these two bugs will play a very bigger role in our research. I'll talk about that how and why in a while. It is my sense of my responsibility to acknowledge all my team who is working with us, helping various aspects of this research. Some of them are here today. Like, for example, Dr. Alka Jagesar, she is here. She is one of my postdoctoral fellows. Dr. Panikumari Paritala is somewhere back. And Teja, she should be here, but I don't know where she is now anyway. So, one thing I would like to draw your attention is about multidisciplinary nature of the team. You will realize today's real world research is not one discipline, not one area. You work beyond disciplines. That's how we'll be able to solve many real life problems. Actually, another topic I'm passionate about is airport security research, which I did simultaneously. Professor Tiwari mentioned I was the project director. There we have researchers from 40 disciplines: architecture, civil engineering, chemistry, physics, mathematics, statistics. But anyway, you can see that I briefly touch upon the areas of the people here. Professor Michael Schultz is the orthopedic surgeon, he's a trauma specialist, and Funny is a biomechanical and biomechanics specialist. Professor Kristen Spine, she is a virologist, and Alka Jagesar is a chemical engineer by training, but now she works a lot on antibacterial surfaces. Jafar Hassan is a biotechnology guy, but he does a lot of work in this tissue engineering. Hazrin is a biomedical engineer, and Teja is a respiratory virologist. She's just getting training doing a PhD. And Janani is a microbiologist, and Hisham and Asha are both biomedical background. Basha is mainly polymer chemist. You can see that how people of different backgrounds working on a similar project, on the same project, to achieve a common goal of producing bactericidal surfaces. So those of you, some of you know your findings in your own way, and you will realize that how important to bring multidisciplinary people to solve a real life problem. So all of them have a significant contribution to various aspects of the research, which we'll see over the next 20 or 30 minutes time. And it's again a bit of marketing in my university. Those of you who don't know, we never traveled to Brisbane. This is a beautiful Brisbane city. This is Brisbane River. This is our university, Queensland University of Technology. We have two campuses both places. Generally, we do a lot of engineering and characterization, everything in this campus, but a lot of bacterial studies and medical studies we'll do in the other campus. We call the Institute of Health and Biomedical Innovation, which is a very, very leading institute. These are some of our facilities in various aspects. To give a brief background, I'm trained in manufacturing engineering, mechanical and manufacturing. However, these are some of the areas I work on is interdisciplinary areas, which are tissue engineering, permanent scaffolds and orthopedic applications, and fracture fixation algorithms. Please remember, most of them will work with medical specialists and also specialists from other disciplines. This particular project is mainly related to nanotechnology applications for better implants. We'll see what I mean by better implants and other aspects soon. These are my collaborators in various aspects of this project, both within Australia, outside Australia, working with a number of them. What I would like to do is first 5 minutes just show some light on various medical implants in human body. Then I will spend some time clearly how we are changing the current status of the medical implants for not only for better productivity and also to minimize any orthopedic infections due to post-surgical issues. So you can see that this is we have implants for every part of the human body. It could be a bionic eye, a bionic ear. It could be any parts of the scaffolds. Could be lost leg, lost arm, and you can see some problem here. There is issue of osteosarcoma. I'll show that more detail later on. Knee joint and hip. So there are several implants for every part of the body. So one of the primary issues at the moment is, I see differently statistics in two countries, which is Australia and India, and we realized almost up to 20% revision surgery are because of the post-surgical infections. We need to go for secondary surgeries, or even 3 times. I have some statistics we'll share later on. So what we are looking at is how to improve quality of life, particularly in aged population. Talk of arthritis, talk of hip replacement, knee replacement, all happen during secondary stage of life, which is 60 plus years. So, but what is happening currently, we realize almost 20% cases the infections are coming post-surgical time, which causing a lot of issues. So what we did is, we were working in this area over the last 5 to maybe 7 years, and Alka and Funny all they finished the PhD is working different aspects of this project. So what we realized is, how can we minimize what is the current practices, the surgical practices? If you're putting implant, they coat with antibiotics, or they treat the patient with heavy antibiotic dosage, which leads to another major problem in future, which is antibiotic resistant superbugs, what we call as superbugs. I'll talk about it later. So what we realized is, how can we learn, how can we look at this issue by looking at nature? If you see, for every problem human being faces in real life, there is solution in nature. I mean, those people who had, could be Germans, could be Indians, have ancient traditions of treating. They realize that every Ayurvedic way or homeopathic way, there is a way you can treat every problem. So by looking at it like that, we want to see, is there any solution for this kind of a problem? Then we suddenly realize the 2 bugs I shown, cicada, dragonfly, gecko skin, shark skin. Some of these things have particular behavior. When the cicada or dragonfly dies, its main part of the body flush disintegrates within a few months, whereas wings will stay a few years perfectly without any damage. What we realized is, then we looked at the wings, we looked at this, studied them clearly, and realized they have a particular structure called nanopillar structure, which try to kill any bacteria come in contact, kills the bacteria instantly, and also some hydrophilic surfaces don't allow bacteria to stick. So these are some of the things what we realized. So what we are trying to do is biomimic those surface structures on the implants, thereby implants will be self-antibiotic or bactericidal, which doesn't need any other treatments, any other antibiotics. That's what our researchers proved in the laboratory environment. And now what we did is, the scope of this study is beyond bacteria. If talk of, for example, you are talking about coronavirus today, how can we treat, how can we stop spreading the virus one place to other place, one person to other person? Coronavirus is basically, with some current understanding, it is mutated from a bat, a virus carried by bat, and it is transferred to humans now. So what we are looking is, in case of most commonly infections for us is influenza, flu, whatever we get, and other forms of infections we get easily. So what we did is we extended our study beyond bacteria, and can we use these surfaces to deactivate viruses also. We tried most common orthopedic viruses, which is RSV, rhino, and other viruses we tried. So that's what we share for next few minutes, some of work done. So you can see these are some of the implants for orthopedic applications. I don't want to go through all of them, but to give you an idea, these are the dental screws. I mean, even very often when you go for a extraction of a teeth, or you have a root canal treatment or other things, then suddenly pain will come back in a week time due to infection. So again, whatever research we are doing could address some of these problems. These are some of the cranial implants. People who tumors grow in the brain, and what we need to do is we need to accommodate the growth of the tumor. Otherwise, the rupture of tumor could cause catastrophic death of the patient. So what we do is using 3D printing technology, we do special purging to accommodate the growth of the tumor in the brain. There are different structures we use actually, this kind of structures we use for better osseous integration. And here are some examples. So this is a typical case in Australia. This particular guy have osteosarcoma is a very rare form of cancer. Unfortunately, it's a bone cancer. Generally, it doesn't affect younger children, but in this case, this guy's all the rib cage is gone because of the osteosarcoma. Then this is we use a 3D printed special case to bring its functionality as normal as possible. And similarly, you can see that commonly it probably will come in this cup, a cracked cup or cracked ball, which is a common problem in the beyond 60 years in the aged population. So you can see the another abnormality in the skull and create some issues. So these are some of the, this is again we use implants for personalized, customized stents for human beings for cardiovascular applications by using 3D printing process. And this again, some other aspects you can see how you can see that how the implant design you can do it, customized implant based on the blockage of the arteries for different patients, and that implant is done by 3D printing by using titanium. And similarly, implants we use not only for vascular applications, but non-vascular applications also. And you can see even in the brain, you can see blood vessels in the brain are so thin, and you can produce implants. This you can see the size of the thumb, and you can see the size of the implant so small. This wire, the diameter of this wire is very, very small, less than 0.01, is less than 10 microns. So there are various applications of implants for different aspects. So just basically I want to give you what is our role. So being a manufacturing engineer, that would have shown clearly how our work will be beneficial for different implants, but it doesn't matter anyway. So now, given the background of different implants, what we are trying to do is trying to produce special nanotexture surfaces on these implants, thereby the surfaces will be self-antibacterial and will also help for better osseointegration between one implant design. So this is my brief coverage of my talk will be here. As I mentioned, focus of this presentation is not only bacterial surfaces production, but also how these structures could be used for antiviral applications as well. You can see healthcare infections are a huge number. In Australia alone, the statistics are about 6 to 7 years old. Australia alone will have 165,000 infections per year. And imagine the amount of downtime, the amount of cost will be in the order of a few billion dollars, including actual surgical costs and patient downtime. And it is caused by mainly as a bacterial infection or viral infections. So you can see the several ways. The infection contamination could start anywhere in the IC, intensive care units or hospital departments, or it could be as simple as the lift buttons in hospitals. You go, somebody infected, particularly coronavirus, has the lift button, you go on that same button, you could contaminate very easily. The operation, what we are doing is trying to generate special surfaces on all these components. You can see several parts of the operation theater. Thereby, there will be bactericidal surfaces, they kill impact all the bacteria, virus, and infections instantly. This you can see that this is the usual way how the bacteria and viruses will spread. Could be through one-to-one individual by touch, or could be droplet form to the environment. So some of what we're doing is we use both kind of surfaces. Some restrict the sticking of the bacteria, some will kill bacteria on contact immediately. So I already mentioned about superbugs, which is the antibiotics resistant bugs, which could be normal bugs like Staphylococcus, Pseudomonas, or E. coli. What happens is these bugs will get to mutate into different form. There will be a stage will come, no antibiotic and will kill them. If you see today, as of today, you see Australia, I got statistics from Australia, Europe and America, almost they spend few billions of dollars in treating these antibiotic resistant superbugs. And if you see the future is very, very scary. We think today cancer is a big problem for us, but few years time, cancer could be very easily treated and lifespan could be expected. But the biggest worry of the future is these antibiotic resistant superbugs, which once people get these bugs in their body, they have to die. There's no way of treating them at this stage. So this is the biggest, these are some of the examples you can see how different forms of the antibiotic resistant bugs will impact. So what we did is we tried with our surfaces, we tried some of these antibiotic resistant superbugs and we killed them within 7 minutes. But again, we'll show some of our tests in a minute. Again, you can see both anti-biofouling surfaces where bacteria cannot touch the surface but still in the environment, and bacterial surfaces where bacteria, as soon as come in contact with it, will die immediately. And we proved that in our studies, we proved that very clearly they could die within short period, as little as 7 minutes, or within an hour. Almost most of them are disinfected dead. There are two kinds of surfaces we are looking in nature. One is a shark skin, a lotus leaves, or also dragonfly wing, or cicada wing. First two types are mainly produces microstructures, nanostructures, which could, structures at macro scale, which will mainly anti-biofouling surfaces where it prevents sticking of bacteria, whereas both the dragonfly and cicada will actually lead to bactericidal surfaces. They kill all the bacteria or deactivate virus within 7 minutes of contact to the surfaces. We studied all these aspects individually. So far, 4 of my students completed PhDs and several aspects of production. Outcome is a process called hydrothermal synthesis, a chemical process to produce these nanopolar surfaces. And basically, what we did is we learned from nature how we can design, better surfaces on implants, thereby they could be bactericidal. And we, as I mentioned, we studied both cicada wing and dragonfly wings, and we did surface characterization, and we studied bacterial studies by attaching bacteria to different surfaces and how they kill. We studied the bacterial mechanisms as well, and also then next step then we mimic the surfaces by inspiring nanofabrication and titanium implants, and also we extended to hospital surfaces on different grades of aluminum material. Basically, based on this concept, we went for the grand nano design about nanotopography and antimicrobial activity, which kills any bugs attached to these implant surfaces or hospital surfaces. You can see some of the examples here is cicada wing. You can see wing have a hexagonal pattern with the nanopolar structures. The pattern is so uniform. Any bacteria come in contact will be killed very, very soon within a short period of time. We did studies few minutes, half an hour, 1 hour, several hours, and the next slides will present how long it takes to kill completely most of those things. So you can see this is the structure actually, nanotexture surfaces on these wings. They have wings will have different surfaces, wings have different surfaces, different textures. What we did is we worked in optimizing best nanostructure which could deactivate a virus, which could kill bacteria which in contact with the soil. Similarly, look at cicada wings. So what we realized here is when I said bacteria, it could be gram-positive, it could be gram-negative, it could be spherical, it could be round-shaped. Only gram-negative got very weak structure here, whereas gram-positive have several layers of peptide protein layers, which takes longer time to kill them. But what we proved in our studies, actually, alcohol proved in our studies, both gram-negative bacteria were killed very, very quickly with the nanostructures what she produced by using hydrothermal synthesis process. And you can see we also tried same thing for the dragonfly structures. You can see here, dragonfly also has no nanostructure, but the only thing is the spacing is not as uniform as cicada wings. So we can see SEM pictures and CRSM images. You can see what we see is here bacteria is completely active and alive, and on the structures, once you put bacteria on these surfaces, you can see rupture at the diaphragm and cause leak of cytoplasm and bacterial cells that die. What you can see imaging, all red indicates dead bacteria and green indicates live bacteria. That's what we tried for different 1 minute, 5 minutes, 10 minutes, 30 minutes, and then this is 60 minutes. We tried different time intervals, and you can see as the time interval increasing, almost most of the cells are died, which are green before they died here. And also what we realized is, you can see by looking at this diagram, the rupture point here is approximately about 4 minutes. Actual killer bacteria starts dying within 4 minutes of coming in contact with the nanopillar surfaces what we produce. And I'm not sure this will work or not.
It's working.
It's working? It's working.
Yeah, it's working.
So this is only a graphical simulation we did, how exactly these nanopillar structures rupture the bacterial cells and how the actual death of bacteria happens. I mean, there are several mechanisms. We ourselves learned, we thought this is one way bacteria dies, but after 3 years we realized, no, it doesn't happen in that way, it dies another way. And I presented that work in the 30th AMC in Singapore, and the same room and same ship, but in Singapore. You can see that this way actually finally happens with the bacterial cell that happens completely. So you can see that the nanostructured dragonfly is here. Dragonfly is only difference of cicada is they also have nanopillar textures, but they are not as uniform space. The geometry is quite different. They have the dispersed geometry, but it will still kill the many commonly bacteria causing autoimmune infections. However, the death rate will be slower than other process. We also did the FTIR analysis mainly to make sure. Another question came to us: is there killing is happening due to just bacterial geometry, nanopillar geometry, or any chemical compound which present on the wings causing the death of bacteria? We realized absolutely there is no chemicals. FTIR analysis clearly proved there is no chemicals. Entire killing is happening due to biophysical model, the interaction between the geometry of the nanopillars and bacterial cell diaphragms. That's where actually that is happening. And you can see that so all the cells very active and spreading around here. They are very live cells here, but once you put on this dragonfly nanopillar structures, they rupture and die quickly. You can see that same thing happening here. Almost most of the cells are dying within less than an hour time. And now what we are doing is, while we are doing this the work we showed so far, mainly we did titanium surfaces by using different techniques. It could be hydrothermal synthesis, it could be electron beam lithography, or it could be helium-ion milling. Several techniques we tried. Each one technique is mastered by one PhD student. But now what we realized is, those techniques what we studied are expensive. They're justiciable on implant surfaces. But implant surfaces are very small in nature. It could be maximum few millimeters size. But if you want to do hospital surfaces, where the hospital bag is about almost 2 meters long by 145 centimeters wide. So then we were thinking, can we apply this technology and can we upscale to larger operations by using different, like aluminum sheets of 3 meters by 2 meters long, and even aluminum complete walls and handrails, several things what we tried. Then basically most of these nosocomial infections, our intention is mainly to find a way of minimizing hospital-acquired infections. Currently what is happening is most of the hospitals use different microbial elements or use some swabs to clean the surfaces regularly. But the problem with the swabs is that the bug get resistant and become superbug or antibiotic resistant bugs. That's why using continuous application of antibiotics doesn't help. So that's why we're trying to find another way of killing all those bacteria cells attached to that. So in this case, what we did is we tried several aluminum alloys, which are commonly used materials for various structural applications, in construction applications, in hospitals, building industry. So you can see at what we did is we used a proprietary our own technique, which is much similar to wet etching, but we used our own process, See, after 10-minute interaction treatment, you can see the kind of a post has been formed. As up to we did up 1 hour and 3 hours, then we get perfect nanopillars here, which are coming in contact. What we did, we studied all of them. We made sure at what stage entire bacterial death or the virus deactivation happened. But these are the 4 points we tried. So then also we tried another. What we realized is, in this case, we realized that we are getting only microstructured pillars, not nanoscale, and that's not good enough to kill, because bacterial cells are nanoscale. They can slip through those, they disintegrate the pillars, and they will survive. So then what we tried different materials, aluminum 5052, the multi-scale reference. Again, we tried 10 minutes to 180 minutes. You can see that structures are getting better. We are getting a combination of both micro and nanoscale structures. And we also, what we did at this stage, we studied different bacteria. Basically, E. coli is a mutated superbug, and we tried that how we can see that initially only 16% of cells are died out and survive, which is in the control surface. And once you can see that as you go down, when this is aluminum 1200 is microscale one, so it's not killing, a lot of bacteria is still alive. Whereas we went to aluminum 5052, the death is happening up to 80% now, you can see that. So 80% of bacteria is getting killed within an hour time. Then we tried a different material to aluminum 5042. So here we tried multi-drug resistant bacteria. As I mentioned, you can see this pneumonia bacteria or E. coli or Pseudomonas arizona. These are the ones that are not original form, they are mutated, no antibiotics can kill them now. But we can see that through our studies we realized that we can kill those kill these superbugs which are multi-drug resistant mutated bacteria. We realize we can kill them as well. You can see the comparison between control surfaces and tissue plates and actual nanostructures we produce. And also we tried another third category of aluminum alloy. End of the day, what we are doing is, what alloy will give us the best nanopillar structure which could kill bacteria almost 100%. I mean, we haven't got 100%, we got up to 91-92% killing, but we're quite happy with that outcome too. So you can see this AF images gives the surface toughness, what generates on the structure from 1 minute small level to 1 minute to 3 hours. Then you can see that other impacts, how the itching from half an hour to 3 hours will generate best roughness. The roughness is the one causing the roughness leads to the better formation of the nanotexture surface, nanopillar surfaces. They are in turn killing the bacteria, deactivating virus. So you can see that, as I mentioned, we also did surface chemistry to make sure, or TF4 and the other analysis, we did make sure actual death of bacteria is happening just because of the nanopillar geometry, not because of any chemicals which present there. So you can see that initially cells were alive and active, happily living here, but you can see that after putting on a etching surface, 3-hour etching surface, all of them dead spread around. Initially you can see that confocal microscopy imaging, all the bacteria is alive here, but you can see once put on surfaces, most of them kill. I mean, there is still some green spots. This is only 50 micron structure, but the next one you can see. Sorry. Anyway, you can see the comparison here. Almost we kill 91.9% of the bacteria by using etching surfaces. Where the control surface only 3.2% of bacteria get killed. We did for both Pseudomonas and also Ceros also. Now we extended this study to 2 other viruses with respiratory syncytial virus, RSV. You can see the initially bacterial virus level is so high, and as the exposure goes down, you can see almost we got down to 90% level of viral activity. And actually, further extended study beyond that, then we realized complete viral will be deactivated. You know, virus is not like a bacteria, it's not a cell. They only can deactivate them. So we also tried the same study for another rhinovirus, and you can see that how the level come from down level to here. So probably we are the first in the world who extended study to virus, with a few other groups working for different bacteria. So please remember, our scope of our study is really limited to only bacteria and virus which causes orthopedic infections. That's where our study is limited. So we also studied the mechanical properties of these etching surfaces End of the day, we know the nanopillar structure will generate the excellent killing 90% bacteria. But what is the time scale? Will they kill today? How about next week, next month? We need to, end of the day, we need to prove the long-term viability of the structures. We did nano inhibition, we went to very high loading, and we did the loading for 30 minutes. Still our structures was, if you see these images, you can see the structures are still intact. So the structures are destroyed under the 12,000, 2,000 nanotons impact, but you can see the nanotons are still intact. That what it clearly indicates that this structure does loss, but how long we still, now we know up to, we guaranteed even Alka with her study, she realized up to 6 months those nanopillars are very active and killing the bacteria, but we are doing a long-term scale now, how long we can last, 3 years, 5 years, 10 years, which is important to actual transfer technology for application. Also another thing we are studying is, at this stage we studied we studied separate environment to kill the bacteria. We studied different environment, how the osteoblasts will survive and where osseointegration happens, and so but we now another thing where our Alka and other researchers are looking is mainly co-culture studies. We put bacteria and live osteoblasts, same environment, and what we want to prove is it kills not only bacteria but enhances morphology and osseointegration and survival of osteoblasts. That is a study we're going on now. And what basically brief summary is we use Pseudomonas, SRS and RSV virus, all of them kill between different time intervals between 7 minutes to 3 hours. And we also proved that at 2000 micronewtons, we'll be able to disengage the structures are lost very long, almost as long as a few months. So basically, at this stage, what we see is the epidemic, the outbreaks could be what we have in coronavirus. It was SARS few years ago. All these are the epidemics, and we are hoping this nanotechnology will help us to get to fix those problems which is caused by the epidemics. Could be bacterial infections or viral infections, and that's what we're hoping that nanomaterials will be featured to address most problems. I'll stop at this stage, and I sincerely thank you for your attention and thank for the organizer for the opportunity.